This is my 16th video on helping people study for Actuarial Exam 2, but it's the first video where I'm going to talk about something called the force of interest function. It's problem 1.6.2s in Broverman. For a given discontinuous force of interest function, find the equivalent nominal rate compounded quarterly. And here's the problem statement. Customer is offered an investment where interest is calculated according to the following force of interest. Maybe you know what that means, maybe you don't yet. Just hang on. Here it is. It's a piecewise defined function. If you graph this function as a function of t, the variable here is in the subscript, as is common with actuarial notation actually. If you graph this thing, it would be a discontinuous function, so it is a discontinuous force of interest, whatever that might mean. The customer is investing 1,000 at time 0. What nominal rate of interest compounded quarterly is earned over the first 4-year period? What is an equivalent nominal rate of interest compounded quarterly for 4 years? I could call that I4. By the way, that's not a power, that's just a superscript with parentheses indicates that's an interest rate, a nominal interest rate compounded 4 times per year. All right, I want to do two things here. I want to basically just tell you, first of all, what to do and solve the problem. That's for people who know a little bit about forces of interest already. I will do that first. Even if you don't know about the force of interest, you can still follow what I do. And then in the second part of the video, I want to talk about what a force of interest really is. So here's the goal. You need to solve the following equation. Solving this equation for I4 will give you the answer to the problem. 1,000 times 1 plus I4 over 4 to the 16th power. What does this represent? This represents the future value of 1,000 at nominal annual interest rate I4 compounded 4 times per year for 16 periods, which if interest is compounded 4 times per year would be 4 years. This needs to equal 1,000 times, okay, here it gets a little strange, e to the integral from 0 to 4 of this force of interest function. Okay, so this is an equation that we need to solve for I4, and we can completely evaluate the right-hand side. So then we would divide both sides by 1,000. Actually, we can do that right away and take the 16th root, then subtract 1, then multiply by 4 to solve for I4. So let's do the integral on a separate line here. The integral of this force of interest function from 0 to 4. Well, it's a piecewise defined function. You can integrate discontinuous functions like this that only have jump discontinuities. We need to integrate the first piece that goes from 0 to 3 and has this formula, 0.02t. And then add the integral from 3 to 4 of the function. It's got a different formula over that interval. It's just a constant function, 0.045. Doing the first integral, integrating 0.02t gives you 0.01t squared. That's going to be evaluated from 0 to 3. Integrating this constant function gives you 0.045t. That will be evaluated from 3 to 4. This is going to give you, let's see, 3 squared is 9 times 0.01 is 0.09 minus 0. I'll go ahead and put the minus 0 for emphasis, but of course you don't have to write that down. And the second one is going to give you 0.045. If you're unsure, you can go ahead and do it this way. That is the same as 0.045. So in the end here, the right-hand side, after the 1,000 is canceled, evaluates, the integral itself evaluates to 0.135. That's what the integral evaluates to. So now my equation becomes 1 plus I4 over 4 to the 16th power equals e to the 0.135. Take the 16th root of both sides, subtract 1, then multiply by 4. Let's just do that all in the calculator. What will I4 equal? What will the answer be? Here's my calculator. Watch carefully what I do. Yeah, this is something that I haven't done before. I'm going to use e. The e to the x function is above ln. I've got to use the second button and then press ln to evaluate e to the x. I type in the exponent itself first, 0.135, do second e to the x is the ln button. There is e to the 0.135, you can check that. I need to take the 16th root of that. 1/16 is 0.0625, so I can raise this now to the 0.0625 power. That's the 16th root of e to the 0.135. It will equal 1 plus I4 over 4, so now I subtract 1 and multiply by 4. The answer is this, 0.03389, approximately 3.389%. Right, that is the answer. All right, let's spend the rest of the video talking about what exactly is a force of interest function. By definition, delta sub t is the instantaneous relative rate of growth of your investment. Instantaneous relative rate of growth. Now, if I didn't have the word relative in there, if it was just instantaneous rate of growth at time t, the answer would just be the derivative of my amount function. Typically, the amount function is called a of t, so its derivative will be a prime of t. However, the word relative is in there. Really, this should be interpreted as a rate of growth as a percent of the current amount, so I need to divide this by a of t. That's what the force of interest is. It's the instantaneous relative rate of growth of your investment. Actually, if your investment is going down in value, a prime will be negative. This can be a negative quantity, and that would indicate that your investment is going down in value. A prime of t itself, again, would be the instantaneous rate of growth. Relative means it's as a percent relative to the current amount. You've got to divide by the current amount, a of t. A of t is the amount at time t. All right, so that's the definition of delta sub t, the force of interest. Could we use this equation to solve for a of t? Could we see how a of t is related to delta sub t in a different way? Can we solve for a of t? Yes, you can, and probably the quickest way to think of it is to think of this expression as the derivative of the natural log of a of t. Now, that's not something that's necessarily going to pop in your mind right away. It's something you need to realize. I mean, certainly if you do differentiate this thing, natural log of a of t, with the chain rule, you will get 1 over a of t times by the chain rule, a prime of t. You will get exactly this. But realizing that that's true is not something that pops into most people's mind right away. It's something to learn. By the way, before I go on, an alternative approach to trying to solve for a of t is to realize this is really a differential equation that you could write as dA dt equals delta sub t times a. You could also think of it that way, and you could separate variables to solve for a of t as well. But I'm doing it this way. What I'm going to do now is I'm going to integrate both sides of this equation, this equaling this. Integrating this thing is supposed to be easy because it's the integral of a derivative. You're going to get the original function back. Actually, thinking of it in terms of the integrating from one number to another, you're going to get the difference of this function, natural log of a of t, at one value minus another value. I'm going to change the name of the variable of integration. I'm going to call it tau. So I'm going to write the integral from 0 to t of delta sub tau d tau must equal the integral from 0 to t, where t is an arbitrary positive number, of this dd, I'm going to go ahead and use a tau here, dd tau of natural log of a of tau d tau. Okay, why am I using a tau here? Well, ultimately I want my capital A of t to depend on t, where t is an arbitrary fixed positive number, so I really want to have my true variable for the function I want to solve for in the upper limit of the integral, which technically means I should use some other variable for the integrand, and tau is the Greek version of t, so I like using a tau, but other people use different letters. They might use a u or a w or whatever. This thing, again, is the integral of a derivative by the fundamental theorem of calculus. This is going to simplify to natural log of a of t minus natural log of a of 0. And this thing is just an integral of an unspecified function. Just leave it as is. By a property of logarithms, the difference of two logs is the log of the quotient, like this. And now I can solve for a of t ultimately by exponentiating and then multiplying both sides by a of 0. Let me also rearrange here. We get a of t divided by a of 0 is e to the integral from 0 to t delta sub tau d tau. So a of t is the initial amount, a of 0, times e to the integral from 0 to t delta sub tau d tau. Think about how this compares to what I did when I solved the problem back up here. A of 0 is 1,000. I went ahead and used a t there instead of tau. It's, you know, the upper limit of that integral was constant, so I could use a t here. That is the same thing I have down here with a of 0 being 1,000, t being 4, and then using a t instead of a tau up there. All right, so that allows you to solve for a of t. By the way, in this example, you can certainly write this thing as a piecewise function. You could, in calculating this, do the integral in two cases. One case where t is between 0 and 3, and one case where t is bigger than 3. And let's see, I did it ahead of time. In the case where t is between 0 and t, the answer for this integral ends up being, well, 0.01 t squared. And in the case where t is bigger than 3, I'm looking at what I did ahead of time if I can find it, the integral ends up being 0.09 plus 0.045 times t minus 3. That would be the piecewise function that is the exponent of e. Then making it the exponent of e in this formula, you can ultimately find your simplified formula for the function capital A of t. And actually, that's an alternative way to solve the problem. You can ultimately find what a of 4 is and set it equal, once again, to 1,001 plus I4 over 4 to the 16th power to solve for I4. But I wanted to introduce you to the idea of a force of interest here as well. Let me also say that in this case, let's come back up to the original force of interest. When the force of interest is constant, in the second case here, 0.045, that is actually exactly exponential growth. When the force of interest is non-constant, and in particular when it's increasing, if you graph this force of interest function, it turns out to look like this. When it's not constant here, when it's increasing, that actually corresponds to faster than exponential growth, at least if that kind of increasing behavior in the force of interest continued into the future past t equals 3. When the force of interest is constant, that's exponential growth with continuous growth rate actually of 4.5%. When it's non-constant and say increasing, that ultimately is faster than exponential growth. Another insight about the force of interest that you should know.